Good afternoon, classmates. In this report, I will explain to you how industrial drying works, different kinds of dryers, and their applications. So let's go on with the types. Now, dryers or drying comes with several types. There's batch drying, continuous drying, and their subtypes. Now, if you studied heat transfer, you'll be familiar with these terms: cross flow, counterflow, and co-current flow. And there are others like freeze drying, spray drying, and microwave drying as well. So let's start with batch drying. Batch drying means a batch of products will be dried first, and after that another batch will come in. This is good for small scale farms because they don't have much products anyway. So how this works is that products will be inserted to the drying chamber, and they will sit on top of the perforated floor. By perforated means that there are lots of small holes. The holes are small enough to keep the grains from falling to the plenum. Now, plenum means space with air. It allows the hot air to blow through the products and dries them. Next, this is an example of bean batch dryer. This is how it looks like in real life. Next one is column batch. It's a more complicated type of dryer, but it is more efficient because the products, mostly grains, are heated from the inside. So this is the cross section of this dryer, and the hot air will go through it, and it will go through its sides. Now there are several applications of these dryers, but this includes rice, wheat, grains, or whatever grain based. These are usually seen on farms, these dryers. Now let's go on to continuous drying. Now continuous drying has several types as well, not several, just three. And I will skim over them one by one and I will explain them later. So first one, cross flow, next counter flow, and concurrent flow. Now, by cross flow means that the direction of the products to be dried is perpendicular to the direction of the hot air. So as you can see here, the granules or the products that are need to be dried go to this fluidized bed. Now, it's called fluidized bed because wet products act like fluid when they interact with hot air. Now, this part, this fluidized bed, is actually run by a conveyor. So the granules will come in here, and then the conveyor will push the products. So it causes the products to move while it's being dried, and will go out as dry products. Counterflow. Counterflow means that the direction of the products is anti-parallel to the direction of hot air. This is rarely used because this has the tendency to overdry the products, which causes it to decrease its quality. But the good thing about counterflow is it is efficient. So we will use less fuel to achieve the same amount of drying you'll get. But it requires heavy supervision so that the products won't be over dried or maybe burned. Next is co-current flow. I don't have any animations or pictures of co-current flow, but this is an example of co-current flow. This is a cannabis dryer, marijuana dryer. So the products comes from this part to this part, so left to right, and the hot air blows from left to right. So they're in the same direction, they're parallel, they're co-current. That's why it's called co-current flow. Now, this dryer is called rotary dryer. So it turns, it rolls, and the products will move from left to right or from whatever direction it needs to go. This is what it looks like inside. So there's a screw type thing inside. It's called flight or flights. I don't know why they call it flights, but that's their name. That's the name of the part. So this is the diagram that shows the components of this cannabis dryer. So there's the control panel, the heat conveyor, the hopper, combustion blower and gas burner, this part, combustion box, the direct fire rotary dryer is the one that I mentioned earlier. Knockout box was number 8. This is the material discharge, this part, this small part here. 9, cyclone, exhaust stack, and induced draft fan. So I'll explain how the flow works. So the weeds will be loaded in the conveyor. They will go to the hopper. Hoppers are, if you're not familiar with hoppers are like this. In Tagalog, they're called embudo, really big one. And they ensure that the products will actually go to the dryer. So it's feed hopper and auger. This auger part, sometimes the products get stuck in the hopper. This auger ensures that the flow is continuous. Oh, next one, combustion blower and gas burner. This is the part that will produce the hot air, which goes to the combustion box that sends the hot air to the rotary dryer, direct fire rotary dryer. Now, there are two types of rotary dryers. There's indirect and direct fire. In direct fire, the air is heated, and when the air is heated, the hot air directly interacts with the products. In the indirect, it's like fire tube boiler. So the there's a heating element. Okay, there's heating element, and the air will blow through it and will come out as hot air, and that's the hot air that will be supplied to the dryer. There's the knockout box. Most of the weeds will exit here, the knockout box and the material discharge part. But there are two things here: weeds and the hot air. But we only need the weeds. So how do we separate them? So the weeds will drop in here, and the hot air will go in to this pipe, to this part, and some of the dried weeds will come with it. That's why there's this cyclone. So in the cyclone, number 9, the hot air with weeds will move in circular manner, spiral. Since they move in that manner, the centrifugal force will cause the weeds to go out and stick to the walls of the cyclone. So it's like this. Say for example this one, okay? So I will turn this. As you can see, the rotation caused the material to go outside radially. And that's what happens with the weeds as well. And that separates the weeds from the hot air. So the weeds will come down here, will be collected, and the hot air will exit here at the exhaust stack. Of course, we want to make sure that the direction of weeds and the direction of hot air are in the opposite direction. That's what the induced draft fan is about. Now, their differences. So as I mentioned earlier, if you have studied heat transfer, you'll be familiar with these terms. So there's cross flow, counter current, or and co-current flow. So the difference is in counter current flow, this is the best when it comes to heat transfer. It's so good that it may over dry the products. In co-current flow, it's not that good. Some of the hot air that will exit are still full of thermal energy, but it's more friendly when it comes to grains. Cross flow is like the medium point of the two. So whether you choose cross flow, counter current, or co-current flow type, it depends on your products. Depends on uh, how heat affects the products that you will dry. So applications, weeds, of course. And if you're not familiar with this is called biosolids. This is what comes out of sewage treatment plant. So in sewage, it's a liquid, and the solids are separated from the liquids. The solid part is dried and becomes this biosolids. It's a fertilizer. It's popular among farmers. So that's it for continuous drying. So let's go with spray drying. In spray drying, the liquid products are sprayed. So let's say the product that you want to dry is milk. So it's liquid. It will go through this atomizer. It's like spray, like this. You can see this. That this is what it means to atomize. It sprays the product to this drying chamber, and hot air will come through here, and it's only it's only meant to be used for products that have to be powderized because the hot air is around 200 degrees Celsius. But it does a very good job in drying the products. So, applications. Pharmaceuticals, if you want to make medicines, you can use spray dryers or milk for kids. Okay, so let's go on with freeze drying. Now, I believe all of you have taken thermodynamics too, so you should be familiar with this. This is the TS diagram. I don't know if you encountered this in your thermo one, the pressure temperature diagram, but this is simple. So how freeze drying works is that it freezes. Let's say this is the product that needs to be freeze dried. It will be frozen first. The lower will be pressured so that the ice will sublimate and heat will be applied so that it will sublimate completely faster. To further explain that, look at this TS diagram. So you will start with products that has liquid water. So as you reduce the temperature at constant pressure, it's just 1 atmosphere. So you lower the temperature, this is sensible heat. The liquid will drop its temperature, go to ice liquid phase. This part is latent heat. So the liquid will turn into ice. The ice will lower its temperature even further. So if you're freeze drying, you need the solid ice to go here. Ice vapor gym, you need it to sublimate. But how do you make it from here to there? So to explain that concept, let's look at this pressure temperature diagram. So let's say you have a liquid substance. It has initial pressure, initial temperature. Since you already taken thermodynamics too, you should know what will happen to the boiling point of liquid, liquid water, when the atmospheric pressure is decreased. So you have liquid water, experiences 1 atmosphere. Let's say you put that liquid into a vacuum chamber, what will happen? So if you lower the atmospheric pressure, say you lower it from here to there, what will happen is that it will be easier for the water molecules to fly out as vapors because it's vapor pressure versus atmospheric pressure. Since you lowered out the atmospheric pressure, the vapors or the water molecules can freely fly as vapors. So this is what happens. The temperatures the temperature of water is around 23 degrees Celsius, but it's already boiling. It's been placed inside the vacuum chamber, pressure is lowered, and doesn't require much energy to boil off. It's gas. Next. So in freeze drying, so product starts with liquid water and it was frozen first. So this initial temperature moved to the left and final temperature makes it solid. Pressure is still atmospheric, still ambient. Same thing happens with ice, except instead of liquid to vapor, it will be solid ice to vapor. So if you don't know what looks like, this is what it looks like. This process is called sublimation. So if we're talking about water, liquid water to vapor evaporation. Solid ice to vapor sublimation. This is dry ice. That's dry ice. It's solid carbon dioxide. Now, carbon dioxide normally exists as gas. So, for the dry ice, our atmospheric pressure is just low pressure. That's why it instantly turns into gas. So, how it works is that, like what I said earlier, the products or the food will be frozen. The pressure will be decreased to vacuum around 100 to 500 millibars, somewhere around that level. So the ice will start to sublimate. It will naturally sublimate, but takes a long time. So it will be heated. It will be applied to the product so that it will sublimate faster. Now, before I continue, I will explain the story behind this um, cycle that I got earlier. There was a flood somewhere in Houston, America. In a university, their documents were flooded, and the people wanted to preserve the documents. So what they did is they freeze dried, but in a different style. They lowered the pressure first. So as the atmospheric pressure decreases, the water turns into vapor. Now, as you decrease the pressure even more, you'll go to this line called triple line. Triple line, the water will exist in three phases: solid, liquid, and gas or vapor. If you lower the pressure even further, the liquid portion is gone. Now, if you don't know what three phases looks like, so let's say this is the liquid that will enter three phases or triple line. Some of them will turn to ice, some of them will stay liquid, and some of the water will be gaseous form. So in this part, it's actually already sublimating because it is in ice vapor part. But as you continue, to decrease the pressure, the ice that is sublimating will cool down even further, reduce its heat energy, and it will turn into just solid ice. This see this black point. They intended to do that, to turn it into block of ice, so that the bacteria will be killed because the documents were flooded. After that, they applied heat, and all of the ice were sublimated. And the gas, the sublimated gas, heated even further, and they applied heat so that the documents will be in room temperature again, but without the water. It's been freeze dried. So that's the story behind it. I hope I'm making sense. Okay, next. Okay, so I mentioned earlier that the products are heated. So there are three ways to heat the products: infrared or light rays. Then the infrared is invisible light, just like ultraviolet. Next one is the microwave, and the third one is conduction. Now, the best among the three choices is microwave because it can penetrate through the object. It doesn't just heat up the outside and uh, keeps the inside from being cold. Microwave affects the particle. So imagine this particle that's going up and down. That's the particle that is going to be microwave. So whether it is outside or inside of the product, it will be heated evenly. Now in conduction, let's say this is your product. You see, this part will be heated first, and the products on this side are still cold. Same with infrared. But in infrared, it works in products that doesn't have even surface, since it's just a beam of radiation. In conduction, the product has to be relatively flat for it to be effective, so that it can conduct heat in higher surface area. Okay, applications of freeze drying. Now, freeze drying is expensive. It's around 5 times the cost of normal drying. So, the applications of freeze drying must be pretty special. So, if you look at these pictures, these are the pictures of foods that are eaten in space. So, there are astronauts in space. This is the food that they eat. These are freeze dried. This is called the astronaut ice cream. This is ice cream that is freeze dried. These are, if you look at this part, see there's this pouch and there's this tube. This is where the hot water comes in and it rehydrates the freeze dried food so that it can be eaten again. But these are frozen solid, as in they're really dry, they're really hard. So they're not only used in space foods, they're also used in military. The good thing about freeze drying is that when you freeze dry something, it will last for several years. Let's say you cook adobo or caldereta and you want that food to last for several years for some whatever reason you have, freeze dry it and it will last almost forever. So yeah, it's used in military. Now MREs, if you're not familiar with them, it means meals ready to eat. So it contains freeze dried foods. The soldiers will put hot water and it's ready to eat. Next is microwave drying. Now, in microwave drying, it's like continuous drying, but it uses microwave instead of hot air. They have batch dryer type as well, batch variant of microwave dryers. Now, this is the diagram. It shows how it works. So, the products will go through here using a conveyor. It will move while it's being dried by microwave. Now, as I said earlier, the advantage of microwave is that it evenly heats the products from inside or outside, and it gives the microwave dryer a flexibility. Let's say you have big products, small products, it will work just fine. They will be heated evenly. Unlike in hot air types, the ones that I discussed earlier, they will heat up the outsides and the inside will remain colder. So that's the advantage of microwave. So I already explained this earlier. The microwave will influence the particles to move up and down this manner. Whether it's, let's say your product is this big, the particle is inside, it will be heated same way as in the surface of the product. Say you have a big, um, I don't know, let's say ceramic or rubber, and those are ones of the applications. It's rubber, ceramic pots, um, mushrooms. These are mushrooms. Beans. So as you can see, small size, medium size, and big sized products can be dried by microwave dryers and green tea as well. So that's the end of my report. If you have any questions, please ask me. So that's all. Thank you.